Okay, this is the source. Let me write source. Who is that source? Let's not bother. This is the source. So it is moving with a velocity Vs, and this is a detector. Is at rest. The source will generate a wave, and when it be detected, when the source is at origin, the wave will be detected. Is asking together find the apparent frequency of the wave. This is at t equal to 0. It will generate a wave. It's then SU Verma. Let me only explain it rather than giving as a question. So now at this at t equals 0, it will generate a wave. The wave will propagate. And when it will be received, by the time the same concept, no, let me take this one. So by the time it is, when source is here at origin, it will continue to move with this one at certain time t. The detector is going to when source is at origin, the waves will be received by him. Any Doppler effect formula, can you apply it? So I'll give some distance. So let this be L, let this be B. I'll give some coordinates. So what is the condition? The detector is going to receive the waves at the instant when source is at origin. So when it should have been generated? Prior to this one, no? So what is the condition here? At an instant when the source reaches origin. So what this source, it will generate a waves. By the time the source is at origin, the waves are received by the detector. He's asking what is the frequency of, what is the apparent frequency of the waves when the source is at origin, I'll write it. Find the apparent frequency. Find the apparent frequency of waves detected by detector. Okay, what to do now, how to do. So the F is the frequency at which it is generated. By the time it is detected will be F dash. How to calculate this F dash? For that, the theta is needed. So what is the apparent frequency formula? F dash is equal to, detector is at rest. So what is V? Speed of sound. Okay, now look at this one. V. What is the speed of the source is Vs, no? And there's a line joining the source and detector. Am I right? There's a line joining source and detector. So therefore, what is the velocity of source I should take? Vs cos theta. Because in the Doppler effect formula, the velocity of source directed along line joining source and detector should be substituted here, no? So therefore, there should be Vs cos theta. Got the idea? This one. So what is cos theta? Cos theta, we can write it as cos theta is equal to L by R. What is R? R is the distance propagated by the wave. So what is R here? Like a propagation distance. I'm using word specifically. The distance moved by the wave. Propagation distance it is called as. So like this, let me substitute this cos theta So how you define t? How you define t? So the distance moved by the wave in interval of time t. So that Vs should be equal to L by t. So in place of cos theta, what we can write it as? L by t now Vs. Substituting this, the apparent frequency will be Vf, V minus cos theta will be Vs by V. So now slowly you try to get a problems where the wave will take some time to propagate. The wave what happened needs some time to propagate and reach the detector. Means the moment wave generated by source will not immediately what happened will be detected by detector. It all depends upon the distance. If this is 10 meter, this is like a 20 meter, then in that case what you say, what will happen? The moment signal generate will be received. No, if these are like a kilometer, this is 4 kilometer, this is like a 3 kilometer, then 5 kilometer. So definitely what happen, the speed of sound is 340. To propagate 5 kilometer around it needs around almost 16 seconds. So the moment signal generated will not be heard. So sir, when to think like this, when not to think? When the distance between source and detector, if it is of order few kilometers, then definitely when the signal generated at that instant only will not be detected by detector. Getting the idea? It all depends upon the separation between source and detector. If the source and detector are separated by few meters, like few hundreds, like a 100 meter or 50 meter, no, in that case what happen, the moment signal generated will be heard by it. Or few tens, 20 meter, 30 meter, no, okay, fraction of time it will take sound to propagate, then we need not to bother. The separation is between source and detector is large, no, then yes, the wave will take some time to propagate. There's a background is needed. Getting the picture. So these are the types of numericals what you can expect your student has to work out. Here only. So some questions like I could have asked. Okay, this one. Find the number of beats heard by the person. I'm asking beats. Why beats will come? Find the number of beats heard by the person. Why the beats idea will come? Say he will receive one direct wave of frequency F1. He will receive the reflected wave F2. The difference of that is what we get. Beats. So in the same question, shall I ask you further? Find the number of beats heard by the person means we have F1, we have F2, and we have F1 also. The difference of that will be the beat frequency. I think you have some very good questions in the Doppler effect. And those things you can see very clearly here. Find the number of beats heard by this person. You will receive F1 and F2. So you have F1 and F2. Take the difference of these two will be the number of beats heard by the person. So if you want, you can add that also. Find the number of beats heard by the person. Means what we should do? Just F1 minus F2. That is enough. In Doppler effect, some questions are there like this also. You have to take difference. Sir, shall I plot intensity versus time graph? Yes, if you have a time, you plot it. Or else just it's only F1 minus F2, no? That is sufficient. Find the number of beats heard by the person walking between the car and the wall. F1 minus F2, the difference in frequencies. The difference in frequencies between direct wave and reflected wave. That is what the beat frequency. You do have many questions like this in the most of the textbooks what we are referring, no? So do work out numericals. And I think now you get plenty of numericals to work out. They too, they are based on kinematics, no? So tomorrow what we do, we'll take some applications like what we did, no? Like acceleration. We'll go for mixed concept, Doppler effect with the rolling motion, Doppler effect with friction, Doppler effect and projectile motion. So the different Doppler effect and collisions. conservation of linear momentum with a different like a concept for how this Doppler effect can be taken into picture. Doppler effect and SHM. Anywhere I can bring, because the moment a particle moves, there I can call it as a source. You do have wide varieties of questions. It's a very versatile topic. You have to work out different numericals here. The basic concept is what I tried to put everything today. The wavelength, how to calculate apparent wavelength, apparent frequency, when it is moving, accelerating, when the separation between source and detector is very large, then the instant of time at which signal generated and detected will be different, no? Got this? So these are background. So you have to work out many numericals in the books. No? Okay, we'll end up the class. Okay, thank you all of you.
Thank you, sir.
Thank you, sir.
Thank you, sir.